Hi, and welcome to this SIMBA webinar. The topic today is DC Power Flow Controller design with SIMBA and Python. And before we go and sorry about that. Before we go deep in the analysis of SIMBA, I would like to say a few words about SIM. SIM is a Canadian startup. We are based in Montreal in Canada. We do two things. The first one is we provide electrical engineering consulting services. And the second one is we develop SIMBA, the new power electronic simulation tool. My name is Emmanuel Rutovic, and Guillaume, who is online as well, is my associate, and we are together working on SIMBA. So what are we going to see today? First, we're going very quickly to see what is SIMBA. Then we'll see what is new in SIMBA, what we have developed in the last few releases. And finally, we'll go and look at the DC Power Flow Controller design. And by the end of the webinar, we'll have a few minutes for questions and answers. So what is SIMBA? SIMBA is a new power electronic simulation tool aiming to simulate any type of power converters with unprecedented speed and simplicity. The philosophy that we have for SIMBA is to build the best-in-class simulation platform for any converters. So if you're developing a low power converter or high voltage multi-level converter or high voltage grid connected converter, we want to build the best tool for all those applications. For any engineer, if you are a student or a professor in university, or if you are a young engineer working in a startup or a senior power electronics engineer working in a corporate industry, we want to build the best tool for you. And finally, any application. This is the most complex thing. We want to be able to simulate topology, different topologies, use SIMBA to design controller, do and run thermal analysis, run why not code generation and real-time simulation. So our ambition is to build the best-in-class tools for all those applications, any converter, any engineer, and any application. In the idea of building the best tool for all the engineers, we have two different ways of using SIMBA. The first one with a classic graphical user interface, a simple Windows tool that is very user-friendly and very fast. And the second way of using SIMBA is through our very powerful Python scripting API. Today we'll demonstrate the two approaches that are very complementary. I would like to point out that SIMBA is 100% free for universities, for students and professors for teaching and research. This is our business model. We want SIMBA to be used in the academic world, and we are providing free licenses. And it's very simple to get a license. You create an account. There is no contract to sign. It's very easy. If you are a student or a professor, feel free to grab your license to try it out. So, what is new in SIMBA? We released the first version of SIMBA a few months ago. And since the initial release, when we did our first webinar, we have added a lot of very cool new features. We have kind of an aggressive roadmap. We release new versions every month or two, which is, I think, kind of unique in the industry. So we have added C code support, thermal analysis, a lot of new models, including lookup tables. We added global variables. We improved the cursors. And those are just the main new features. We have added a lot of other C things as well. Okay, let me show you a quick demo of what is new in SIMBA. So this is a classic buck converter, but in this case the controller here is designed using our new C code model. So this is the clock that we see here. The controller is a discrete controller that will generate the duty cycle controlling the transistors. So with the C code controller, we can actually edit the code directly in SIMBA. We have a nice C code editor with color highlighting, with which is quite advanced. I can run a simulation and we can look at the results. So when you run the simulation for the first time, it will actually compile the C code directly in SIMBA, and when the simulation starts, it will run the simulation. So we can look at the waveforms that were calculated. I can look at, for instance, the output voltage, and here we can see our new cursors. So on the bottom of the screen here, you can see the metrics of our cursor. If I move the cursor, of course the metrics move. I can specify time stamp for the cursor like this. If I hold the shift key, I can move the two cursors. I can move the two cursors simultaneously like that. So it's very simple to use and very nice. We calculate a lot of metrics like peak to peak, average, and RMS as well. When we develop C code, usually in other tools, it's kind of hard to debug. If you have a bug in your C code and the C code compile, but you have a bug somewhere that makes your controller not working, it is usually kind of hard to debug. That's why we have added the support of debugger in SIMBA. So here I have opened the same file, but I have the same design. If I go back to my model here, I have another. This is a copy of my design. The only difference is I'm using this external file mode, where I point to an actual C file here, and I'm in my IDE, in this case Visual Studio Code, and I am actually debugging my C code. So I have breakpoints. I can look at variables value. For instance, in this case, I am at 4.7 volts in the input of the converter. The current is about 5 amps. The time in this case is about 100 milliseconds. I can specify some conditions for the breakpoints. So the simulation will start, for instance, when the simulation time is about 2 milliseconds. So I can run this, and now the simulation time is, I can see it here. No, I'm not there yet. So it's very nice to oops, I have to apply that. That's one. So it's very nice to use this debug mode to work on your C code, and then when your C code is working and debugged, you can actually take it and put it in your controller. Let's actually stop that. The second thing that I would like to show you is thermal analysis. So we've added to the transistor, to all the semiconductors basically, a new setting called thermal data that allows you to specify losses data of your semiconductor. So I have here my my buck converter, and the bottom here represents the thermal model of the converter. So I have here my junction to case model for the IGBT. Oops. Here I have the junction to case for the diode. Here I have the case to air thermal model, and here I have my voltage sources. I can run a simulation, and we can look at the evolution of the temperature and of the losses here. To specify the thermal data, we have added a new tab here called thermal data in the test bench tab. And here we can actually specify the losses of the semiconductors. So this is the conduction losses of my diode. We can specify it for different temperatures. And what SIMBA does, it actually takes this data, look at the actual current in the diode and extrapolate the voltage and calculate the conduction losses. And we do the same thing with the turn on and turn off losses of the IGBTs, like this. So we have a very accurate thermal model to calculate the losses. Something else that we've added is the support of global variables. So on my circuit here, I can select new variable. I can click on new variable. And what we are going to do is we are going to create a new variable that we'll call Tm, that is the ambient temperature. We will specify a value of 25 degrees, and we are going to set these values on all my capacitors. So I can select my capacitor, and here write Tm. Same thing on my ambient temperature source here. Okay, and I can run the simulation and it will use the value of 25 for the ambient temperature. But something nice that we can do is we can actually create a new test bench, which is a parameter sweep. We can rename it ambient temperature sweep. And here I can select my design. Here I can select global design variables. We select our Tm, and maybe we can make a sweep from -40 degrees to maybe 80 degrees with maybe 5 points. And we want to see the last signal value, so the last value of each simulation versus the parameter value versus the temperature. So we can run this, so it's very easy to run. We can run it here. It will take a few seconds to complete. So what SIMBA does, it starts at -40, run the simulation, calculate the values of all the variables, go to the next temperature, and it sweep the temperature like that. And I can now go in my results tab, and I have my ambient temperature sweep here. For instance, I can look my total losses versus the temperature, which is okay, I will delete this graph and I will start my total losses versus the temperature. We can see in this case it's about linear here. Okay, so this is the new thermal analysis and the new global variables support in SIMBA. I hope you like it. Okay, that was a very quick demo of what is new in SIMBA. Next is we are going to look at DC power flow controller design with SIMBA and Python, and I will Guillaume, the floor is yours.
Okay, well, thank you, Emmanuel. So I hope everyone can hear me. If it's not the case, do not hesitate to leave a message on the live chat of YouTube. So today I would like to show you a short example with which deals with the design of a DC power flow controller. So this controller makes it possible to manage the power flow between 2 decibels voltages, such as in embedded electrical networks for aircraft, as shown in Bowman's PhD thesis. So this, the design of this controller is a perfect example, according to me, of what can be done with Python, and more precisely the Python control toolbox and SIMBA using both its graphical user interface and its Python API. So the principle of a DC powerful controller is quite simple, actually. A DC powerful controller can be realized with two switching cells connected together through an inductor, and the control of the current of the current leads to the power flow control. So to design this DC power flow controller, the first step to be done here is to design a current controller of a single DC-DC leg. So let's start with the graphical user interface of SIMBA to draw the circuit corresponding to this DC-DC single leg control by a PI. So this is a short video I've previously made in order to show you once again the graphical user interface as it's simple. So here we have selected a first DC voltage source, then the two semiconductors in order to realize the first switching cells. Here we are. And then we are going to select a passive element, the inductor, in order to create the current connection, and so on, which leads to this final circuit of a single DC-DC leg with its PI controller. So now let's keep on with the design of the controller itself with Python control package and the SIMBA Python API. So here is my Jupyter notebook. Okay. So here we are. So this is the screenshot of the circuit we are considering. Okay, let's evaluate these first cells. So these are the parameters of the circuits. Okay, here we are. So here, this is the block diagram of the model we are considering here for the current loop and here for the controller. So the closed loop transfer function can be computed with this analytical expression, and which leads to the values of the coefficients Ki and Kp. And so targeting some values of the damping coefficients and of here under the speed, we can compute proper coefficients, proper value of the coefficients of the controller. And so that's what we are. That's what we are doing here with a value of the damping coefficient of 0.7. Okay, so here we are. Okay, so these are the values of the coefficients, and now let's check with the use of a step response in the Python control toolbox. Okay, so here we are. So here, something which is quite surprising is that we can notice here an overshoot of around 20%, which is probably not acceptable. So maybe this is due to the zero of the transfer function here. So here we can use the basic map function of the Python control toolbox to check that. Here we are. So, and indeed here we've got a zero, which is very close from the real part of the pulse, which explains, okay, this exceeding overshoot. So to solve this issue, there are different solutions. For example, we can increase the values of the damping coefficients, or we can design another controller with a zero compensation. So let's try the first solution and perform a sweep of the damping coefficients to evaluate this influence of the overshoot. So that's what we are doing here. We compute, we are making here a for loop, and we compute the values of the coefficients, and then we plot the step response of this transfer function. Okay, here we are. Okay, so here we can notice that yeah, for damping coefficient of 1.4, it seems to become a good compromise, good trade-off, okay, between the overshoot and the speed of this system. So let's try to perform this parameter sweep in order to check the behavior with the SIMBA simulation this time. So here in this zone, I load the project. Okay, here I load the object of the controller, which I've designed in SIMBA, and then this is the controller, the PI controller. And in this for loop, okay, I modified the values of the controller. So here we are. Okay, a few seconds to plot it. So, and here we can check that, okay, for damping coefficients of 1.4, we've got an offshoot which is much smaller than with the initial one. So let's keep on with these values, and if necessary, we can also compute, okay, the coefficients of the discrete controller. Here I've used the Destin method in order to compute the A0 and A1 coefficients. Okay, so yeah, so sorry, here we are, these values, and now we are going to perform the SIMBA simulations and to check the behavior between the continuous controller and the discrete controller. Okay, so here we are. In green, this is the result of the continuous controller, and here the discrete. So we can notice here that the discrete sampling, okay, introduce here a slight offshoot, an adding overshoot, but that's okay for this example. So now let's keep on with the step 2, that's to say the design of the DC power flow controller. Okay, and so we can go back to SIMBA in order to design the full circuits. So of course I've already done this circuits. So here we are. Yeah, so this was the circuit of the continuous controller. This was the circuit of the discrete controller, and here this is the circuit of the DC power flow control with the 2 switching cells, and here the controller, the discrete controller, okay, which makes possible to control both duty cycles of each switching cell. Okay, so now if we go back to the Python book, here we are. So this is a screenshot of our circuits, and let's try to, and here we are. So in green we've got the power reference, and in red this is the estimated power. So we can see that in steady state the behavior is okay, because it follows the reference. But on the other hand, this overshoot here can be a little bit annoying. So in this case, maybe it could be very useful or more convenient to design, a controller with zero compensation. So maybe this will be shown in the next webinar or in the next part in LinkedIn. So to conclude with this example, this is a perfect example of what can be done with SIMBA, and with from a transfer function which is computed analytically. And I think that in the future roadmap we are going to develop and to propose the AC sweep feature of SIMBA, which will lead to a simple model of the transfer function this would be much easier to to get this transfer function, and it will avoid the computation of an analytical computation of the transfer function. So yeah, that's all for the next example. Thank you, Emmanuel, and I will give you the floor back.
Thank you, Guillaume. That was super cool. So yeah, we can have a little bit of time for questions and hopefully answer. I would like to remind you that SIMBA is free. If you're a student or professor, you can go on simba.io and request your academic license. You can also you can also request a free trial of the software. Will simply create an account on simba.io. So we have a question from Marcel. I don't see any sample rate and discretization issues mentioned. Would you like to answer this question, Guillaume?
Can you repeat a little bit the question?
Actually, I can answer. So basically, the way it works for now is for digital control, we use the C code block, and we have kind of a default template for Z domain transfer function, and we use an external clock. So you can specify basically the sample rate that you want, and the Z domain transfer function will be evaluated at a given sample rate. And this is completely independent. This will work fine even if you use a variable Timestep solver. We are working, actually, this is not public yet, but I can give you a secret here. We are working on a new control solver that is multi-rate. That means that different model can have different time steps, and this will allow actually to have even more performance for digital domain transfer function and blocks like delays and sampled block, basically. Let us know if we have answered your question. And if any of you has a question, just let us know. We'll be pleased to answer the questions. Anyway, another question: can SIMBA import any SPICE model or XML from power devices? So SPICE model, we don't support that for now. And I don't think we will, to be honest. But it might change. However, because we don't want to have a SPICE solver, because SPICE solvers are they are very good and widely used, but they are very slow. So we are working on a new switching transient model of semiconductors, but that will not be compatible with SPICE for switching transient simulation. Then for XML from power devices, we are actually working on it. That will be released in maybe, I hope, by the end of the summer, maybe the month of September. This is basically the capability to load XML data from manufacturers in the thermal data of SIMBA. We don't support that for now, although it is possible to use the Python API to populate the thermal data from the XML data, but this is not officially supported. Let me know, Firman, if we have answered your question. Another question from Prabat. Thank you. Does it have support for real-time simulation using platforms like Launchpad TI? The answer is no. We don't support real-time simulation for now, but it will take time until we'll get there. But I hope we'll get there one day. Okay. If you have any other questions, feel free to ask. Otherwise, we would like to thank you again for your time this morning. I hope it was interesting for you, that you enjoyed it as much as we did. So Thank you again, and have a very nice day and a very nice afternoon wherever, or very nice evening wherever you are. Thank you again. Talk to you soon. Cheers.
Bye.
Bye-bye. Thank you, Guillaume. Bye. Oh, other questions. I thought it was over. Wow, too many questions. So another question: can SIMBA try to simulate on real-time simulation platform? We would like to. This is not supported today, but we would like to. We first want to build the best offline simulation solver. We still have a lot of work to do for the offline solver. It would take us maybe 6 months to 1 year. SIMBA is already extremely good, extremely fast, but we're still missing some important features. So it will take us maybe 6 months or 1 year, and then when we'll get there, we'll investigate real-time simulation and see what we can do for that. A question for you, Guillaume, from Eren. Do you see the questions?
Yeah, I answered the question. I'd say the question is if the sample rate is near the switching frequency, there should be spatial problems. Well, I'm not sure of what you mean by this question, but the fact is that the sample the sample rate is exactly at the switching frequency, because the idea there is that the degree of freedom, okay, the degree of freedom is the duty cycle, and the duty cycle can be refreshed at every sampling period, and which is the switching period. So that's why, well, usually the sampling rate is set according to the switching frequency of the power converter.
And
I hope I've been clear.
And maybe because maybe Marcel, he has a special topologies or special controller with a variable frequency or something like that. So maybe, and that's where the sample rate is fixed. Yeah. So in this case, I don't see why having a different sample rate and the switching frequency will be different. Will cause a problem. Maybe there is something that I don't see, but basically SIMBA will replicate what is in real life. So I don't think we'll have any issue with that, Marcel.
No. I can also say a few words about my experience with multi-level converters. So in these cases, where we have different switching cells which are interleaved, it's necessary to provide a sampling rate which is higher than the switching frequency. And usually this sampling rate is set as the product between the number of cells which are interleaved and the switching frequencies. That's to say, for example, if you have 2 switching cells which are interleaved, then you have to sample it at twice the switching frequency.
Thank you. Another question from Eren. What about reverse recovery effect of diodes? Is there any plan to implement reverse recovery model for diodes? So 2 things here. We can actually simulate already the thermal losses from the reverse recovery using the thermal model that we have implemented. But it's not possible yet to see the waveforms, to simulate the waveforms. This will be available in I think 2 or 3 months, somewhere in September or October, when we'll have more detailed diode and transistor model. Another question of Srivatsan, sorry if I misspelled your name. Can we use multiple C code block and sync? You can use multiple C code block, and if by sync you mean to have the same clock, basically, yes, it is possible. Okay, so if we don't have any other question, we'd like to thank you again for your time. I hope you've enjoyed this webinar, and I hope to stay in touch with all of you. Thank you. Have a good day. Bye bye. Cheers.